Hello and welcome to this week's edition of the Taurus Report. I am Joe Bakos, and today we are going to take a look at Wolf-Rayet star 140 and try to explain why this star has these concentric rings around it that are composed of ejected dust from the star, and also other dust that might have been in the system. So why are these rings so well defined and concentric, and why do they have a squarish shape to them? This is the Wolf-Rayet star WR140. So Wolf-Rayet star 140 that the James Webb Space Telescope, JWST, recently took this picture of this star. And the interesting thing here, if you look at it, there's two things that are interesting. First, around a Wolf-Rayet, these stars, they eject dust periodically. And because the star is rotating, then normally the dust will come out from the star and form sort of like a spiral, and this spiral might be deformed by various forces. And so that is normally what you see. Now, in this case, with WR140, that is not what we see. What we see is very well defined, concentric rings around Wolf-Rayet, which is extremely unusual. And then the other odd thing about it is that we have sort of a squarish shape to those rings. And so, as always, I will include these links in the comments so that you can all take a look at these articles for yourself. But it has astronomers stumped, and I notice that when I go to the Wikipedia page for this star, if I go to that page, and the interesting thing to me about it is, as you read about it, there's just all kinds of information about, the characteristics of the star, the spectra from the star, the type of dust orbiting it, the fact that it's a binary, and how the stars, this star and its companion, the binary companion, how they might be affecting these orbits and so on and so forth. But really, to me, the most spectacular thing about this are the two items that I mentioned. How are they so concentric like this? And why are they kind of squarish in shape? Those are the two things that I think are the most significant. And any article I've seen, other than saying that's a mystery, it really doesn't, they don't really, dwell on this topic much. They don't dwell on it much. And to me, that is sort of mystifying, because it seems obvious to me that there is some sort of challenge to standard gravitational models here. And so I would like to explore that a little bit. And the thing that I'd like to take note of is that many years ago, an astrophysicist looking at my work claimed that it would be impossible to get stable orbits from such a law. And so this astrophysicist did me the favor, a kind favor, by the way, which I very much appreciate, even though he was trying to disprove what I was saying. He did me the favor of using my force law, a wave-like force law, on a model of the solar system to see how the planets in our solar system would behave according to this type of force law. And so I'd like to show you his results first before proceeding. Now, I would like to emphasize about this the results of that simulation that I'm about to show you, I'd like to emphasize that this happened like 2 years ago, like in or more, something like the year 2000, something like that, a few years ago, or 2021. So several years before we saw this image from Webb, we saw a simulation with a gravity force law, CGC-type gravity force law that produced square orbits. So let me show you this, the results of this simulation. And I will put these up on my website. So this blue spirograph, kind of crazy spirograph, was the orbit of Earth, according to a CGC force law that was used. The green was, or actually, let me see, I got that wrong. I apologize. So the green is Earth, and the blue is Mars, and the red is Venus, and this black is Mercury. Now, the only thing that I would like to point out about this is that obviously these do not match the way that the real orbits operate. But a few comments about that. First, when this CGC force law was first proposed, astrophysicists were insisting to me that you could never get stable orbits from this type of force law. Now, after this first initial try, I was able to get very stable circular orbits using this force law. So this was like a sort of a first try that I proposed, and then an astrophysicist tried my first rough guess in a simulator. And the interesting thing is, I mean, obviously these are not matching the real orbits, but it is interesting to note that instead of flying off into space at some large angle, the planets do actually stay in orbit around the sun. Now, the interesting one was Jupiter. Okay, and notice Jupiter's orbit. Under this simulation done several years ago, Jupiter's orbit was square. And that was very interesting. But at the time, I mean, I didn't think it really had any applicability. So when we fast forward to today, several years later, lo and behold, we see the Webb telescope showing these concentric rings, and also that they have kind of a squarish shape. And so I'd like to share with you how you might verify that a CGC force law can produce squarish orbits, because I have a gravity simulator that I found online from Test Tube Games. And it's qualitative. I mean, the simulator uses what they call sim units, which are kind of imaginary units. But all of the controls for this simulator are very intuitive, and I think they did an excellent job on it. And I do want to say, just as a disclaimer, that I am not connected in any way with Test Tube Games, and I don't receive any commission or anything from your downloading their simulator. Now, their simulator, if you're doing just basic gravity, their simulator is free. They have an online free version, but with the free version, you cannot adjust the gravitational force law. But if you download the full version, then you can change the gravity force law. And the thing is, the good news about this is that the full version, it only costs $7. And like I said, I have no connection to them at all, so I'm not getting any sort of compensation. But I found the cost well worth it. And you get this simulator that is, it's not like the simulator that professional astrophysicists would use. But as I said, it's very intuitive. And it does give you an excellent, just qualitative feel for what happens if you play around with the gravitational force law, and you can do it like super quick and try different laws, see what happens, and so forth. So I would like to show that to you, how to download it, install it, and so forth, how to put a CGC force law into it, and how to run the simulation that I've got that shows square orbits. So let me just show you that right now. The first thing you need to do is get to my site, and you can get to my site always by, if you open up a browser and just type torus report, all as one word, torusreport1word.com, and press enter. And then that should take you to my website. Now I've added a new page to the site. Notice again, for those watching for the first time, I just want to remind everybody to download the paper on CGC, 23-page paper, giving a presentation of cyclic gravity and cosmology, along with the relevant equations to adapt general relativity and all the explanations of it. You would click on this link here. And then this video series, you can find a playlist on Spotify, on YouTube, on Facebook by clicking the links. Now, the one that we're going to look at today is the simulator. If you click the simulator, then it brings you to this page. And here I've put directions on how to run a gravity simulation of your own. It includes directions on how to download this program from Test Tube Games, and what to do once you get there. So step-by-step instructions on how you can get the simulation that I am about to show you. And I'm not going to read through every step right now, but you can find it all here, and it will tell you exactly what to do. So I'll just do it kind of quickly. So down here is a button that you can click on, and that brings you to Test Tube Games. Whoop, I guess I wanted to do it in another tab. So I'm going to right click and say open link in a new tab so that I can keep my tab. So here at Test Tube Games, you can, this is the gravity simulator page, and later on, once you get it installed and you start playing around with it, you may want to come back to this page, because over here in this left-hand column, there's all kinds of tips and directions and everything on the various things you can do with this simulator. The various types of systems that you can set up and different things you can do. And you may want to come back and explore all these links. But for now, all you would do is go down here and download the gravity simulator that costs $7, and leave a tip if you want. And then download it and install it. And once you have it installed, okay, I'd like to show you step by step what to do. Once it is installed, then this is what you should see. I already have it installed on my computer, so I'm not going to go through the whole installation here. But once you have it installed, then this is what you should see. You'll come to this spot, and then you would hit this build button. And the first thing I'd like you to do, if it's not paused, is I would pause it first before you do anything. Okay, so the first thing you're going to do is pause it. Well, actually, the first thing you're going to do is just escape out of this. This is just a test just to see that you have it installed, because there's something else you have to do first. So once you install it, you open it up here. Then to get out of it, you just press the escape button once to get here. Press the escape button again. And then once you press escape, then it should close. Okay, now the reason why I did all that is I wanted you to just install it first and just test that you have it installed. Then come back here to my page, and what you need to do is right here you want to copy all of this. You just copy this. So I'm going to grab it here and copy all of it. And these are the settings you're going to need to demonstrate the square rings simulation. So I will copy this. Now once that is copied, then you should open up the simulator once again. So here is the simulator. Then I go here and I press build. And they'll have something here. And what you should do is just press pause. And then this X for clear. To clear whatever is there, just clear it out of there because we want to do our own simulation. Now to do that, we're going to go over here to this save button. And then you have all these different things. These are pre-made systems that you can explore later at your leisure. But for right now, we're not going to do any of those. You can explore those on your own. Right now, what we want to do is just delete everything that's here. Make sure it's on current. Oh, by the way, yeah, you want to make sure that over here on the right-hand side, you go to current. And then over here, you want to delete whatever is there. And then just paste what you got from my website. So we paste that. That is my simulation. And then down here, we're going to press load. And it's going to say, do you want to save these changes? And you hit OK. Now it loads it. And we should be paused already. If it's not paused, you want to pause right away. Okay. And so this at the center here is the star at the center of this solar system. And then these are planets that are revolving around it. Now, down here in the lower right is the settings button. You want to expand that out. And we want to put trails on. So here's trails. We check trails on and then close the trails dialog box. Then we're going to go to time. And we want to set it to 10,000. So we'll set time to 10,000 very fast so that we can see the formation of these squares quickly. Okay. And then once you've got that all done, then what you want to do is do this quick save over here on the left. And the reason why you do the quick save is that the quick save will save the settings that I just did. And if I don't do the quick save, then when I reload it, I would have to do all those settings over again. Okay? And I don't want to do them all over again, so I hit quick save. Now, by the way, you can see whatever the gravity force law is by clicking on physics over here on the right. And then in here, you can see what the force law is. Well, this is part of the force law. The basic force law is up here, right? But you can change that force law to the gravitational constant times the small mass times the large mass times some function in R, where you make up the function in R. And here I have what I put for my simulation. And let us see what the result is using this sort of CGC version of gravity. Let us run the simulation. Now we did quick save already. And now let us press play and see what happens. And so we see that we do get square shapes. So here we have a solar system with a CGC force law where the planets are, circling the star in square orbits, square concentric orbits. Now, if I pause it, then because I did quick save, now I can do quick load, and it will bring it back to the beginning. Now, as I said, if I had not done quick save, then I would have to start all over again, right? Now, you can add different planets. Up here, there's different things you can add, like I could add a planet here. Here's a planet, and I could just put one, let's say I just put one randomly here, hit this select button, and then select it. Then I'd have to put in, and down here's the advanced mode. So I've got a 100 kilogram planet, and I want to give it some tangential speed. So I'm going to say I don't know, let's say point 2, and heading 90 degrees. Okay, then that means that I've given it a velocity heading this way, and then we can see what happens. Okay, now I'm going to do quick save again, just in case it does something I don't like. I can start here again and change the settings. So I'll do quick save, and now let's try playing and see what happens with that one extra planet I just put in. And you can see it has, a very interesting orbit. And notice how adding this one planet has sort of knocked some of the others. It's knocked them out of their orbits. And the reason is because I made them all very light, and this planet was very heavy. So I might want to change that. So let's pause, quick load again. So I go back to this planet. And I made it way too heavy. I'm going to make it as 0.0001 kilograms. So super small, more in line with the other planets I have in this system, so that it will not knock them out of their orbits. So let's do that. And then we'll hit quick save again. And then press play and see what happens this time. And so you can see that the planet has much less effect on the other planets because it's not so massive. I had made it way too massive. But notice the interesting sort of spirograph shape that this planet is making. And so this is the kind of thing with this gravity simulator. There's all kinds of things you can do with different planetary objects. Asteroid fields you can put in. You can do all kinds of stuff. Change the heading and velocity of the planets and asteroid fields. Change the size of the sun. Change the gravitational force law. All kinds of things that you can do. Now, I would like to point out one thing about this exotic spirograph shape. Let me pause this now, and I'm just going to escape out of this. So to escape out of the simulator, you just press escape a couple of times, and then it closes. So I want to comment on that sort of spirograph shape. So under CGC, for the reasons that I explain at some length in my paper, there is a strong tendency over time, over billions of years, there's a strong tendency to force things towards circular orbits. And so as different astronomical objects or different other influences influence a system, and as time goes on, as the eons pass, there's a strong tendency towards circular orbits. But it is not always like that. It's not always like that. For planets that are very close to the star, any sort of temporary influence, like let's say a asteroid goes by, or some other object goes by, or the sun has some ejection of mass or something. Okay, a planet can be knocked into a sort of a spirograph shape, and if it is in a sort of a stable situation, that spirograph shape might be permanent. And so under CGC, having an object close to the sun, like the planet Mercury, having a precession that it does, under CGC, this is not surprising at all. So CGC predicts these kinds of orbits with precession that cannot be explained by ordinary Newtonian gravity. It predicts the existence of such orbits, but CGC is not at a level yet where it could exactly predict the orbit, if you understand what I mean. Like, it would be very much in line with the predictions of CGC that such orbits exist, that you have orbits that form kind of spirograph shapes. That is something that just naturally happens in CGC under certain contexts, which brings me to wanting to talk a little more about the fact of how, in my opinion, the actual way that gravity works would mean that context has a very large influence on gravity, and I want to discuss this once again next. So again, coming back to the Torus Report website, if we go to the home page and go down to the CGC paper and get a copy of that, according to CGC, gravity is actually a waveform with an equation that looks like this. Now, after a long period of acclimation, and I explain what acclimation is in the paper and why acclimation happens, after a long period of acclimation, the force law starts looking Newtonian or similar to general relativity, but it is not always that way, and it is not always that way in all contexts, meaning that depending on the context, we can see variations in the gravitational force law. And so I show what it might look like in something like the solar system. Excuse me, I think I skipped over it. Let's try that again. There. Okay, so here, and here the green dots, and this graph is in the paper. So the green dots represent, this one is Oumuamua, and this is Mercury, then Venus, Earth, Mars, and Ceres out in the asteroid belt. So the purple represents Newtonian gravity, and the blue represents a CGC force law that I adapted for our solar system, showing that it matches up with Newtonian where the planets are. Now, I'm not claiming that the actual gravity in the solar system follows this. I am just saying that a CGC force law can be tweaked in order to match a given context. And in this case, I showed how it could be tweaked to accommodate the planets in our solar system and Oumuamua, which had an anomalous acceleration. But in this graph, it is not anomalous. So Oumuamua right here, falls perfectly on the force law. Now, also, if we look at something like H.L. Tauri, which I've discussed before, under this type of gravitational force law, there can be times, because of this wave form, there can be times when the force of gravity is actually negative. And that means it becomes a force that is pushing instead of pulling. And this is relevant when you're looking at stuff like HL Tauri. This system is a star system where we're seeing planetary formation, and it is my claim that in these areas that are empty of gas in this formation disk, those areas either have very weak gravity or else even repulsive gravity. And so in some contexts, my point here is that in some contexts, gravity might be behaving more as a more purely sinusoidal form instead of a form that just simply decreases with distance, like Newtonian or general relativity. And so in the context of a gaseous disk that's forming, we might see a more exaggerated sinusoidal form. Then, of course, as we opened with today, when you see something like this, right? We look at this and we have things that appear to be orbiting in kind of a squarish shape. And so it is my contention that CGC can explain two aspects of this shape. Once again, the sinusoidal form can mean that in these gaps here, gravity might be either extremely weak or, weaker than standard gravitational theory would allow. Okay, might be very weak, or else even repulsive. It could be repulsive in these gaps. And then we have a squarish shape explained by the CGC force law that does actually allow square orbits. And so we can see that CGC lends itself very well. It lends itself very well to different contexts. And again, I would like to remind the viewers that if one starts looking on the scale of intergalactic clusters at a scale where it seems like all masses are accelerating away from each other, and I've explained in prior episodes where I think some of that redshift can be due to something called the tired light hypothesis, although it's been proven to my satisfaction that tired light cannot explain all of the redshift. But I think that some of it can be explained with that. But the rest of it is not due to stretching of space. It is due to these masses actually accelerating away from each other, which is simply due to the operation of gravity according to a CGC force law. In other words, those galaxy clusters at those scales are actually pushing on each other. And so we don't need to posit the stretching of space at all. And so because CGC is so dependent upon context, and because the reason why the gravitational force law is generated like this, and I explained this in the paper as well, how it is generated by sort of alternating electric currents in the nuclei of atoms. Because it is so complex in the way it is generated, there is no way at this point in time to come up with a simple, elegant gravitational force law that applies in all contexts. And so I am really advocating using CGC, but in the sense that in any specific context, we do have to fall on point plotting and regression to say that, okay, in this context, at this location, and with these objects, gravity is behaving in this way, and then we come up with a force law where we tweak the parameters according to CGC to match up with what we're seeing. Okay, if we see objects move in a certain way, then we make a force law sort of arbitrarily, and I am criticized often by theorists saying, like, oh, you're just you're just point plotting and just matching, doing regression based on the points without having a simple and elegant force law. And that's true. So in that sense, that criticism is valid. But in my paper, I explain the reason why it must be so temporarily, and perhaps more investigation along this line will later allow something like what they're requesting, which I'm not able to do right now. But for now, it is my claim that we must just arbitrarily create a patchwork of various gravitational force laws and just adapt them to various contexts that we see. Like we have one that we might use at the distances of intergalactic clusters. We might have a different one for galactic rotation rates. We might have a different one for the interiors of galaxies, for solar systems that have had time to acclimate for a long time, for gaseous stellar systems that are only just starting to form. The force law might look still different. And so in all of these contexts, we may need a modified CGC force law, a different one for each of these contexts. But once again, the paper explains why that is so. I want to close tonight with switching subjects a little bit, like going off on a different tangent, just because there's a paper that is in the stages of being published that just came out this week, and it is by Alice Shapley and her colleagues here in the UC system in California. And this paper is exploring the metallicity of galaxies as we look back in time. And this, again, is very relevant to, in my opinion, disproving Big Bang cosmology, because by its very nature, the Big Bang is saying that everything kind of started at the time of the Big Bang in this sort of plasma soup that expanded, and then at some point the plasma cooled to become neutral elements, hydrogen and maybe some helium. And then as all these elements gathered together, then the first stars would ignite. Now, the first stars that ignited, according to Big Bang cosmology, would be what are called population 3 stars that are made entirely of hydrogen. And because when a mass first starts coalescing like that, it doesn't have the star does not have the gravitational force necessary to create the higher metals. And when we use the word metals in this context, basically we mean like anything heavier than helium. That's not normally how people use the word metals, but in this context, when you say metals, it just means heavier than helium. So anyways, according to standard cosmology, just cosmology, to form all of the rest of the elements of the periodic table, it takes generations of stars, because the star has to go nova, and then it collapses, and then after it collapses again, it can make something a little heavier, maybe it'll make some nitrogen and oxygen, then it'll go nova and collapse again, and then maybe make stuff like iron. So anyways, it takes several generations of stars doing that in order to produce these metals. So if you start getting close to the time of the Big Bang, if you're looking at through telescopes, and if you look back far enough, that means you're also looking back in time, because it takes billions of years for that light to get to us. So the further you look, the further back in time you're looking. And so if you look back far enough to where you're starting to get near the Big Bang, what you would expect to see as you get close to the Big Bang is a decrease in metallicity, because the first generations of stars would just be hydrogen. And so what Shapley and her colleagues are finding when they look back is that there isn't any evolution in the relationship. Once you go back beyond a redshift of 3, once you go back beyond that, right when we start expecting, right at the time when we're starting to expecting to see a big change in metallicity, right? Metallicity getting less and less and less as you get to these higher redshifts. That's when Shapley and her colleagues, they find that there isn't any change in metallicity, as you start going back there. And so, of course, that finding is totally consistent with CGC, which says that we live in an eternally oscillating universe where metallicity over time, it might vary because according to CGC, we have a cyclic universe. And so things may change in a cyclic way over time. So it's not static exactly. I don't like the phrase static universe because that implies things don't change at all with time. But in CGC, what you have is a cyclic universe. So you may have cycles of change in all of these kinds of parameters. There may be kind of cycles of change. But roughly, the metallicities very roughly should stay approximately the same with time, whereas with the Big Bang, that simply is not the case. And so because that research is just coming out this week, I did want to mention it again, even though I had talked about this topic before. So that is it for today. I want to thank you all so much for joining me again here on the Taurus Report. And goodbye for now.